Thank you very much. I am Adrian Geles, partner at ABUD from Hungary. ABUD stands for Advanced Building and Urban Design, and we are a consultancy firm empowered by engineers, architects, researchers specialized in sustainable building and urban design. And within the COOLIFE project, we have been responsible for the work packaging on comfort, lifestyle, and user behavior for space cooling, for reducing space cooling needs. And I will present our results in the following slide. Why is this topic so important? We also saw in Lucas's presentation that by passive measures and by applying different shading technologies or ventilation, the cooling demand can be reduced to high extent. Occupant behavior is also one of the 6 factors identified by the IEA as influencing energy demand the most. And apart from the occupant behavior, there are also other factors which are also influenced by the occupant, for example, the indoor environmental quality needed or the building operation and maintenance. We can see from studies that occupant behavior can reduce energy demand by 50% in commercial buildings. However, there is also an issue with occupant behavior that it causes high uncertainties in the projections. Studies show that the energy gap between the predicted and actual energy performance is in the range of -38 to +96%. So it is our task or our goal to try to find more precise data and to use these in the predictions to have a more reliable prediction for the future. Within our work, we have 6 factors which we have looked into regarding occupant behavior. The first is the occupant presence. Is there anyone in the building who needs space cooling or has discomfort? And then there are 5 more actions which the occupants do either within their lifestyles or to maintain thermal comfort. And these are window opening and ventilation, shading type and operation of these shadings, equipment use, and space cooling set points and preferences for air conditioning. And also the perceived thermal comfort and adaptation can be influenced by the occupant, for example, by taking drinks or changing their clothing or changing their activity level. We have already completed 2 deliverables, which includes these aspects which I show, and we have separated 3 directions regarding occupant behavior. One is the occupant behavioral patterns. So how do occupants behave? What are their triggers in doing this? And looking into this, we have looked into building-specific aspects, regional practices or differences, what are the assumptions in the standards, and we have also conducted a representative survey for one of the member states of the consortium. Then we have looked into the thermal expectations as the main trigger of using space cooling. We have looked into this from a comfort theory approach. Then we have identified what other social demographic aspects can influence the perceived thermal comfort. And we have also included this aspect within the survey. And then the third main aspect was to find examples how behaviors can be changed, how people can be motivated or nudged to reduce their energy consumption. And I will show this a bit more in detail later. And based on this literature review, what we have done, we have identified realistic assumptions for behaviors, for different behaviors, and we are in an ongoing task where we are quantifying the behavioral interventions for space cooling energy reduction. The first part, which I will show some snippets from, is the thermal expectations and behavioral patterns. We have generated a table including the regional, traditional practices that people already apply to avoid thermal discomfort and reduce the space cooling needs. We have also looked into the standardized comfort requirements. However, in this field, we have found that there is no real difference among the European countries in adopting thermal comfort standards. And also in the legislations, this is a field which is not fully covered yet. Regarding the occupancy patterns, we have also collected information for different building types for where available. So for residential buildings, we have identified a number of time use survey, which statistically shows how the residential buildings are occupied throughout the day. We have looked into office buildings and concentrated on educational buildings, which with their summer holidays have actually a few months when space cooling demand is not turned into energy demand, and this is also not taken into account in the standards, for example. A few words about the survey which we have developed. This is a multidisciplinary survey involving also social scientists, and it is an example that could be replicated in further countries as well, to gather information on thermal comfort and behavior in summer. And we have asked 75 questions in 5 sections regarding the patterns of energy use, schedules of occupancy, thermal comfort requirements people have in their dwellings, and additional information about the location and characteristics of the dwellings and the socio-economic background of the occupants who answered the survey. And a few results which I wanted to share is, for example, that if we see what temperatures are maintained in the buildings, we can see that the majority of the buildings have temperatures between 20 and 25 degrees. However, these are not maintained by active cooling devices exclusively, but a lot of passive measures are already used. And also, if we look into the answers which we got for the air conditioning set point temperature, we can see that although the thermal comfort standards and the legislation generally would assume a 26 degrees set point for cooling, the set points applied in practice are lower than these. We have also asked detailed questions of what passive measures people use during the hot summer days, and we can see that although there is a high percentage of the measures already used, for example, wearing lighter clothes or opening the window only in the coldest parts of the day, there is still a potential in increasing, for example, fan use or by other passive measures which could be promoted instead of active space cooling. And looking into the questions regarding the air conditioning use, we can also see that this is not a constant air conditioning use which people apply in their dwellings, but they activate cooling devices when they feel too hot or only during the warmest parts of the days. Skipping into the behavioral intervention part, we have separated 3 types of interventions which can be used to motivate users to change their behaviors, and we have listed these in the deliverable in more detail. In short, I can say that there are monetary incentives, for example, using dynamic prices for electricity use, which are applicable to shift the peak loads of space cooling demands. We have also found a number of studies where providing feedback and information to the user has resulted in some energy consumption reduction. And also there is an effective tool in nudging occupants where social comparisons are drawn, or the default settings on the air conditioning devices can shift the behavior into a more sustainable way. However, I also have to conclude that the majority of the studies don't particularly tackle space cooling demand, but more the electricity used in general, or concentrate on space cooling, space heating energy demand. So these good examples need to be translated into space cooling related interventions in the future. And then our last part, which is the quantification of behavioral interventions for space cooling reduction. We have, based on the literature, identified realistic scenarios on how occupants could behave or can behave, and defined scenarios for this. Then we have selected a set of buildings which we conducted dynamic building simulation for. In comparison to the previous models you saw from Bruno, this approach is concentrating on the building level, and we have selected building archetypes and building countries which we have run the simulations for, and also done climate change projections for the different locations. And we have looked into individual effect of different actions, and also the combined effect of behavioral interventions with the KPI of what is the reduction in space cooling demand. We have selected the 6 countries during this work, which doesn't exclusively rely on the different climatic conditions, although this is also taken into account, but we also took into account different social and economic situation in the countries. So if you can see on the map that there are six regions, or actually cities, which we have selected: Amsterdam in the Netherlands, Sweden, Stockholm, Innsbruck in Austria, Berlin in Germany, Budapest in Hungary, and Milan in Italy. And we have 3 time scenarios for 2050 and 2080, and we have looked into residential building archetypes and also non-residential buildings, with also considering different renovation levels for these building types. And for the combined effect of the user behavior, we have defined 3 types of behavior. The baseline is the unconscious behavior, where people apply the standard cooling set point, don't use the windows for ventilation in a conscious way. They don't use any shading, and lighting appliances are on the level which the EN standard suggests. And then we define 2 types of alternative scenarios. One is the mitigation, where the occupant reacts to the discomfort condition using these different items that they can access, but don't actively try to avoid the discomfort condition. And then we have the adaptation scenario, where people act earlier and try to avoid the discomfort in advance. And the first results, which I wanted to share, and then you can look into these in the deliverable expected to be published in a month, is that the majority effect, the major factor that has the highest effect from the individual effects was seen to be the electrical equipment use. So this has a very high impact on how the space cooling demand will change in the future, and right now as well. But also there is potential in reducing heat loads by shading control, and also applying ventilation practices, nighttime ventilation, and avoiding the opening of windows in hot periods. And on the next slide, we can see the results of the combined effects in residential buildings for the 2020 scenario for all 6 countries which we have seen. And we can see that already the mitigation scenario could have a very high reduction potential on the space cooling demand. So for example, from the 56 kilowatt hour per square meter demand for Italy, it can be reduced to around 13 kilowatt hour per square meter as a mean. And also we can see on these graphs that not only the mean of the results can be reduced, but also the range in what the different building types and different refurbishment rates can cause the space cooling demand, which reduces uncertainty, which is also a very good goal for example, the electricity network suppliers. And looking into the effect of climate change, we can see that while in the unconscious scenario, the space cooling demand will have a steady rise also in every building type and on every climate, with the mitigation and adaptation user behaviors, these can be maintained in an acceptable level, and also on a level where maybe active space cooling is not even needed for many building types in the future. And this is true for all of the countries which we have looked into. So even in the South climatic condition, there is a huge potential in this. So I would like to thank your attention, and if you would like to read more, please visit our website and read the deliverables. Thank you.